Hi everyone, and welcome to the second lecture of Algebraic Topology in Physics. Go ahead, Pavel.
Okay, so let me briefly remind you what happened during last lecture. So yeah, we kind of had the informal introduction to a notion of kind of homotopy groups of topological spaces with marked points. And also we had considered homology groups of X with some coefficients in G, where G is a abelian group. And yeah, so we and there was a kind of informal interpretation of these homology groups of some sort of networks of n-dimensional defects colored by some elements of the group, and we allow the we consider the model some sort of deformations. Okay, and okay, and maybe there's other like questions about the last lecture. Okay, if there are no questions, let me give maybe some examples of homology groups. Okay, there's a question: what are defects here? Well, I mean, so far we are not we're kind of talking just about geometry, so we consider just something which is locally kind of if you consider our topological space as a manifold, we can always actually there are statements that we can always kind of represent a class in homology by a chain, which is like n chain, which is also a cycle, so it's boundary zero, such that each kind of component of the chain, so each we have these alphas which are maps from delta n to m. So we can always find the existing representative of some sort of class in homology such that like C equals sum ni L alpha such that this alpha I, yeah, this is what I was writing here. Such that alpha I are smooth, kind of smooth embeddings. Well, of course, here, if you assume that M is a smooth manifold. And so basically by defect, I mean the image of these alphas are what we call defects. And when we consider, later we will consider when M is a space-time for some quantum field theory, and then we will see that these homology classes can appear in these networks of defects, appear in some sort of setting where these defects has meaning of extended operators in quantum field theory. But so far, these defects are just kind of submanifolds, kind of the images of this kind of the network of defects is this kind of union of union of n simplices embedded into my manifold. So here in this picture, this is basically union of intervals embedded in M, and more like in 2 dimensions, there will be a union of triangles and so on. Not really. So here we are not using any triangulation, but of course, if kind of one can always if you use fixed triangulation of M, then there also, we can always choose alpha I to be a part of this triangulation. That's true, but at the moment we don't fix any triangulation. So in particular, because of this, because we don't fix this triangulation, we can talk about this deformation of defects as we talked about last lecture. But indeed, yeah, if it's always possible to if you have some triangulation of manifold, it's always possible so that these alphas will be part of this triangulation. So basically, this this is a network of n-dimensional defects. It is what is called will be n skeleton of the triangulation. Okay, and what happened? So yeah, so let me consider some examples. So well, for example, we can consider homology groups of a genus G surface. Kind of a surface with G holes, and then the homology groups something like this. Well, it's not something. Homology groups with integer coefficients are z for n equals in degree 0 and 2, and this is z2g in degree 1 and 0 otherwise. Okay, and another important example is the homology groups of n-dimensional projective space, and let's consider coefficients z2. So this is a quotient of an n-dimensional sphere where we identify antipodal points, and for this result, it's z2. So we consider hm of RPM. So this is z2 for m from 0, 1 to n and 0 otherwise. So next, I want to give a brief introduction to singular cohomology. And this, in particular, this part will be important when we define what is called topological discrete gauge series. So how do we define these singular cohomology groups is the following. So we consider first group, what is called a group of cochains with coefficients in G, which we assume to be an abelian group again. And they're defined as a group of homomorphisms from the group of singular chain with coefficients z to g. And so this is basically has meaning as linear maps from chains to G. Since all the groups here are abelian, the homomorphisms can be understood as linear maps. And then we define analog of kind of boundary homomorphism, which will be a co-boundary here. Boundary homomorphism, which was denoted by delta n, and it will be a map from Cn of x to Cn plus 1 of x. So unlike for homology, we had was mapped from n chains to n minus 1 chains. So here it's mapped from n cochains to n plus 1 cochains. And the definition is the following. So if you have some element here a, which well, it can be understood, a can be understood as a linear map from Cn to G. We map it to a composition of a with boundary homomorphism. And this produces us the map from Cn plus 1 to G. Because if you remember, there was this map, the n plus, sorry, did I? Sorry, yeah. We have a. So the idea is that we first use dn plus 1 to go to Cn, and then we use A, and this composition defines a co-boundary of A. And well, automatically, because due to this definition, we automatically have that this composition of two co-boundary homomorphisms is 0. And so this gives us a cochain complex. Which is again a sequence of abelian groups and maps between them, such that the composition of two subsequent maps is trivial. And then we define, once we have this cochain complex, we define cohomology groups in a similar way. It's a quotient of the kernel by the image of kernel. Sorry, quotient of the kernel divided by the image of delta n minus 1. Okay, so so many of you probably have seen the notion of the RAM cohomology, which has some sort of differential geometric interpretation. And so we can see the RAM cohomology of M. Sorry, maybe I'm keep mixing M and X, but okay, here so far in our context, there are only single logical spaces, just it's called M. And so if M is a smooth, let's assume okay, just assume that this is a smooth manifold. Then we consider space of differential forms of degree n on X. And then we have the exterior differential, which takes degree n forms to degree n+1 forms. And then one can define the Ram cohomology. Sorry, I'll keep x instead of m, should be m. As a kernel of D acting on n forms divided by the image of D acting on n-1 forms. And so these cohomology groups has a relation with the singular cohomology groups due to the de Rhams theorem, which states the following. So I can define a map. Kind of, there is a natural map, which I explain in a moment what this map is. From the Ram cohomology to singular cohomology with coefficients being group of real numbers. And the map, and this map is an isomorphism. The map is defined as follows. So here we take some representative in the Ram cohomology, which is given by some sort of n form. And so we need to map it to an element of singular cohomology. And here we use the following statement. So so if we consider, so in general, so the elements of cohomology, they're represented by some sort of cochains, which are functions, kind of linear functions on chains. But in the case when, and of course, if we if this cochain is co-close, so it's so this delta n is 0, then one can show that it gives a well-defined map from homology, actually from homology classes to the group which we have. So so in general, this map is only surjective, but if the coefficients are real coefficients, this map is isomorphism. So okay, let me write it here. And so if we use this isomorphism, then we need to understand this kind of from this form omega, we need to produce this kind of a map from n cycles to real numbers. And this map is given by integrating our form omega on a kind of on a what one can call a smooth representative in C, class in homology with integer coefficients. So as I said before, for smooth representative means we choose all these maps alpha from n simplices to our space to be smooth. So in general, so in order to let me elaborate a little bit on this isomorphism. So in general, we can consider if you have a cohomology with coefficients in G, we can always define a map from this cohomology to home of Hn x z x with coefficients in G, and this is defined as follows. So we take alpha, so some class of A, where A is a map from Cn. So I keep using this x instead of m. Anyway, so we take the map from chains to G, and we send it to the following. So we need to define a home from homology group to G, right? And we define it as just A, the following way: A of class of some, well, let's see, C. So C is a class. So C is a representative in the class of homology group. And we say that it's equal to, sorry, I wrote it a bit. So this map is the following. So the home, the end of the home is the following: C goes to A of C. So this is a defined element in this home. And the result here one can check explicitly because this map is well defined, because well, co-boundary of A is 0 and boundary of C is 0. So it's independent of various choices we made here. In any case, the bottom line here is that there is isomorphism between the RAM homology of M and singular homology with R. And so you may think maybe this is, in a sense, nicer. It has some sort of more kind of more intuitive to work with. But the problem is that when we, for example, consider homology group with integer coefficients, this in general contains more information about topology of M than homology with real coefficients, which is isomorphic to the RAM homology. So, for example, we can consider three-dimensional topological spaces, which are known as length spaces. usually denoted by LP1. They are defined by quotients of S3 by cyclic group ZP. And for them, for example, we know, so they all have so P is some integer number. So for all P, they have the same homology with real coefficients, but different homology with integer coefficient. In particular, the second homology is isomorphic to ZP. Questions?
Yeah, there is a question on the chat.
Homology. So, well, the notion of for group G, one can define what is called group cohomology. Yeah, there also can be some choice of coefficients. Let's say A. And the statement, so let me to distinguish this is group. So the relation is the following. So this is isomorphic to the cohomology of what is called Ellenberg-MacLane space, the first Ellenberg-MacLane space of G, which is the same as what is called classifying space of G for discrete G. And this is so this KG1. So in principle, there is explicit construction of this topological space KG1. So this is a topological space such that it's the first fundamental group is equal to G, and all other homotopy groups are trivial. Yeah, I guess this, yeah, someone also answered, I guess, this in the chat. So in principle, yeah, it's a there's a relation with this. Any other questions? Yeah, these classifying spaces, they will play a role in this discrete gauge series. So there is another question: is the representative of the group G the element G such that? Sorry, I didn't get in what context. Sorry, I don't quite get in what context this question is a representative of the group. When I'm talking about C is you mean C as a cycle, a kind of cycle representing elements in homology? Yeah, here we are considering this cycle is with integer, is the element of homology with integer coefficients. So it's just a group of integers. Okay, so this this homology groups, they're a bit there was some geometric understanding of homology groups as this kind of network of defects, but the homology groups are a bit less kind of they don't have a direct geometric interpretation, so it may be hard to kind of visualize this if one wants to. What is this? But they actually can be related to homology groups by what is called Poincare duality. So let M be a closed, smooth. Yeah, let me assume. Well, okay, for this I actually don't need smooth, but later I may need. Let me assume that it's a bit smooth. Smooth d-dimensional manifold. And closed means that there is no boundary. Boundary is empty. Then there is the following statement that the d minus nth homology group of M is isomorphic to a n-dimensional homology group of G. And so how this, how can I understand the kind of geometrically this isomorphism? So I'm not going to prove this isomorphism, but I'll give kind of what is intuition behind this. One possible to understand way to understand this is that well, let's take again, consider some chain C representing a class in homology. So again, it's can be understood as some sort of network of defects colored by elements of the group. And so we need to assign to it a class of some cochain. So this so A is should be a map from again Cn x z to G. So we need to define. So given this C, we want to define this map, and so this is generated. This group is generated by, as an abelian group, is generated by freely generated by this maps singular n simplices, so which are maps from delta n to really generated as a abelian group. So because arbitrary element is just a linear combination of these elements, of these generators with integer coefficients. And so it's enough to define then this the value of the cochain on arbitrary singular and simplex. And we say that it's given the following. So alpha is, we can consider kind of the image of this alpha. So for example, here, kind of, well, this particular example, kind of this visualization literally works when d equals 3 and n equals 1. So d minus n is 2. So here alpha is some 2 simplex. And again, let me kind of, since we are just worried about some intuition, so let me assume that this is actually alpha is embedding of delta n to m. And then what we want to do, we want to kind of see, look where this simplex intersects our network of defects which we're considering. And then we sum over all kind of intersection points. So one can write as the following: we sum over I and I. We can, and so we take this ni, which is the element of G, and we take it with multiplicity given by intersection number of kind of image of alpha with image of, let's say, BI, where, so here we take C to be sum over I and I BI. Here, this is alpha. This is, for example, this is the image of B3. Well, and here, to be precise, this is the image of alpha. And here there is like one intersection point. And exactly, you see, so that if like in a generic, so the dimensions add up. So if we can always kind of do some sort of deformation. So these submanifolds, they intersect, they are transversal to each other. So this intersection is well defined. And one can check that due to this definition, let me leave it as exercise. As it from this kind of interpretation, it's clear that delta of A is 0. Any questions?
Yeah, I don't see any question. Okay, there is one. Maybe does the manifold has to be orientable also for this?
Well, okay, let me to be sure. Let me say yes, but in principle, okay. It's well, just for yeah, in principle for Poincare duality, no, it's, you only need it to be closed. And there is a, well, okay, there are also version when it's not closed, but it's modified. The relation is modified. Okay, let me continue with. Okay, let me now turn to some physics applications. Okay, can be understood kind of another example, which is now related to physics. So suppose we want to consider the following question. So we want to consider U1 gauge field configurations on space-time M, and we want to consider them modular kind of deformations. So this means we have some sort of continuous one parameter family of gauge fields. So if you have, if you have two gauge fields from kind of one parameter continuous family, then part of the one parameter continuous family, then we declare them equivalents, and we also quotient model gauge transformations, of course. So mathematically, this is the same as isomorphism classes of U1 principal bundles. Or instead of U1 principal bundles, we can consider complex line bundles. Kind of complex line bundle means this fiber is isomorphic to just C, and this forms kind of defining representation of this U1. Okay. And so the statement that we want to consider is the space is isomorphic to second cohomology of M with integer coefficients. And so this is kind of the isomorphism is provided by what is called the first Chern class. So let me let me first give some sort of what is a physics interpretation, like physics way, physics like a way to understand this first Chern class, and then I mentioned what is briefly mention what is a proper, what is kind of usual mathematical definition. Okay, so before we okay, what does it mean? We have U1 gauge field. So we have so we have kind of gauge field A. So this is a connection one form. And this in general is defined only locally. And we have its kind of field strength or curvature is defined globally. And it's a gauge invariant, unlike A. So, okay, what happens? Suppose we can ask a question, kind of in what kind of maximal subspace of our space-time M we can actually define this A globally. So we can understand, we start with some sort of small patch where A is defined, and we try to extend it. Kind of what is the maximal subspace where we can define. Okay, so there's some questions. So could you please explain why? Well, that's what I'm. Why is the morphism class P1 homomorphic to? Yeah, well, I didn't yet, at least yet, I didn't explain this yet. So, well, what I do now is to explain, like in both in first some sort of physics inspired way and then mathematics inspired way, how to define the first chain class. And then there's a mathematical statement which I'm not gonna prove, that this is some sort of, this gives an invariant of these U1 bundles. So up to isomorphism. But then there is a mathematical statement. This is a complete. In this case, it's a complete invariant, the first chain class for U1 bundles, and this I'm not going to prove. This requires some work. So so the following, then there's the following statement. It is possible to extend. Well, let me not extend, to define A globally on a complement of C, where C is a subspace. Okay, let me write it like complement of the union of images of alpha I, where such that this alpha I, they form a d-2 cycle. So far I'm not talking. Yeah, I'm not choosing any. Well, and I are coefficients coefficient in some group. Let's say G. So far it's not important because we only consider this kind of alpha i's, the singular simplices in my chain. Right? The statement that we can kind of extend to this, yeah, the definition of A to a complement of some sort of network of d-2 dimensional defects. And well, if you consider it Maxwell theory, then you actually should be familiar with the statement. So these defects are known as Dirac strings. So most often this is appears in the context when d equals, and the most classical way it comes in the context when kind of d equals 3. Well, I can send kind of 3 or like 3 plus 1, where the extra time direction, kind of transversal to everything. And we have what is called Dirac monopole. And at some point, this point kind of, okay, this point where the Dirac monopole lives is kind of, there the field of course is not well defined, so it's actually is a kind of physical singularity, so which can be stood as our space-time locally is kind of complement of some point, right, where this Dirac monopole. And then we know that we can kind of in the surroundings, in the space surrounding the Dirac monopole, we can define our gauge field everywhere except some line which goes out of this monopole. So yeah, this is the Dirac string. And so indeed, so this is the case when d equals 3, so d minus 2 is 1, and this is a one-dimensional network. Okay, and but now we actually want to, the next step is to say what is actually values of these ni's, the coefficients in this kind of network of Dirac strings. And they can be defined as follows. So we can consider for each, like around this each alpha, we consider a small circle. Well, okay, it's a circle. Yeah, so this is a, since this is a d minus 2-dimensional, so it has this defects has codimension 2, we can always consider kind of a small circle which links them. So gamma eta is small enough that links eta. And then we, so near, so since our field, gauge field cannot be extended to this to this defect itself, then we but we know that this is kind of these Dirac things, they're not physical, so it's actually artifact of the kind of choice of these choice of the gauge in a sense. So this means that so in the vicinity of alpha I, our gauge field, which we defined everywhere on the complement, can be brought to something, some sort of gauge field which is regular in the vicinity, which we by irregular. By some gauge transformation G. G our gauge transformation. And so we can consider restriction of this G on our small circle gamma I, and this is a function from a circle to U1, our gauge group, which is itself a circle. And then we, as before, we can consider the homotopy class of this restriction of our gauge transformation of the small circle in pi 1 of S1, which is isomorphic to this. And this we define Ni. So after all, we have this way we can construct our d-2 cycle with a d-2 chain which has no boundary. D- cycle in we'll see d-2 m z, and we can consider its class in the corresponding homology groups, which we can ascend as a Poincare dual to second cohomology coefficients in Z. And if you use this isomorphism, this is what gives us first Chern class. So one can understand the first Chern class in terms of Poincare duality as this kind of network of Dirac strings where we cannot extend, to which we cannot extend the one form gauge field. Any questions about this interpretation of the first Chern class? If not, well, let me consider for completeness. Let me briefly mention what is kind of usual mathematical definition of Chern class is that well, here we will use interpretation in terms of let's use interpretation in terms of complex line bundles. So there's a statement that any complex line bundle V on M. So this is a kind of a bundle where the fiber is isomorphic just to C. And again, so for example, one can understand the fields. If you have some sort of fields which have a charge 1 with respect to our gauge field, these fields can be understood as sections of this complex line bundle. So in particular, like is parallel transport in this line bundle is given by this connection A, which you consider. So the statement is that any complex line bundle can be obtained as a pullback of some sort of universal line bundle over CP infinity. So this is kind of infinite dimensional complex projective space. Well, you can understand some sort of it's actually not always enough to consider CPN for large enough n. You don't actually need to go to if you consider a line bundle also with some sort of manifold of fixed dimension, you don't need to go to CP infinity. It's enough to consider CPN some particular large n. So what does this mean? So that there always exists f from M to CP infinity such that this V bundle is obtained as a pullback of this universal line bundle. So this is a universal line bundle is a kind of is what is also called tautological line bundle. So what is a CPN? What is a complex projective space? It's a space of lines in an n-dimensional complex plane, right? Well, for a point in this space of line, we can also change this line itself, right? That's why it's topology. So this defines this topological line bundle over CP infinity, and the pullback. I remind you, the pullback means that so if we want to define some sort of the kind of the roughly the pullback is understood this form. So we have some sort of map the points to define kind of a fiber here over M or some point of M. We take this point, consider its image. So this kind of fiber over X in M. We take it to f of X, and we identify it with the fiber over the image f of X. And this way, this gives us a kind of pulls back the bundle from CP infinity to M. And on the other hand, we can there's a notion of pullback for cohomology. So we have so in general, actually, if we have a F map from M to say N, this defines a canonical map, the F upper star, which is similar to the push forward map, which we consider it for homology group. Okay, let me write it this way: HN M. And so the way to do this is that you take a class of A, and we compose it with F star, which means the following. So A is let me write it in this way. So we have a so this is the element this is represented by home from Cn to G, and well, this is in particular generated by the maps of alphas from delta n, well, the Cn. And so consider let me write this way. So first we define F star as a map from Cn to here I'm omitting explicitly the coefficients, and this okay, this is G. Yeah, let me remove this part. Let me write it more clearly. So first statement is that we define map from F, let's say F star just on n chains, and by taking a generator here and sending it to the composition like this. So alpha is a map from n simplex to m, and this gives map from delta n. And then A here, which is a map from Cn to G, we map it to A composed with this F star. And this gives me a map from CM. So this defines a notion of pullback, which is analog of the pullback for differential forms, which some of you may be more familiar with. And well, the statement, now there is a statement that what is the the second cohomology of CP infinity with integer coefficients is Z, and this is generated by a class which can be called as universal first Chern class. And then the statement that so we that C1, which we want, is a pullback of this universal first Chern class. So this defines element of H2 of M. So this idea we just complete. So in principle, you can just keep in mind for the purposes of what we will have later. You can keep in mind just the first kind of this more like physics interpretation in terms of these defects. Questions?
I don't see any question in the chat. Maybe just about bibliography. Oh, some reference for principal bundles and gauge fields.
Well, yeah, I'm not sure I can give some particular reference. I mean, there are many materials you can find. Okay, let me okay, maybe okay, final thing about this Chern class is first Chern class is the following. So let me make the following remark. So we consider this isomorphism between the RAM cohomology and singular cohomology with real coefficients. The RAM theorem tells us that there is, let me just write isomorphism without specifying the direction. So in particular, we can consider this isomorphism in degree 2. And we also can consider the natural map from cohomology with integer coefficients to cohomology with real coefficients, which induced by the homomorphism from Z to R, which is just inclusion. So since H2 elements of the second of the cohomology are represented by like maps, linear maps on singular chains valued in this group, so we can take we can express the values in Z as values in R. And the statement that if we consider the composition of this map with the Dirac isomorphism, the result is the class of field strengths maybe divided by 2 pi I in the normalization which I'm using. And this is kind of Chern class in the Ramka homology defined by in what is called Chern-Weil theorem. So this is a first Chern class Chern-Weil theorem. But again, as I mentioned before, so this kind of Chern class with homology with integer coefficients, it's in general kind of contains more information. And let me consider a different but somewhat similar example. So now assume that M is not just arbitrary dimension manifold, but it's a closed four manifold. And we can ask about the same question, but instead of U1, we consider SU2 gauge theory. We can see the question about SU2 gauge field configurations, model equivalence, and this is again the same as SU2 principal bundles, model isomorphism. And similarly, we can consider A as a kind of SU2 gauge field, which as one form on M with coefficients being in SU2 the algebra. And so here there's a similar statement we can be defined globally on a complement of a zero cycle in M. So in zero cycles, this is just a collection of points. So what I mean here, C is some, if you write it in this way. These images of alphas are just points. And well, we can do kind of similar argument. So we can consider around each point, we can consider small, well, let me write it as sigma 1, sigma 2, and so on. So sigma I is a small 3 sphere around alpha I. And again, in the vicinity of this point, A is can be related by gauge transformation to some other field which is not singular at this point, called A regular. So here we use a non-abelian gauge transformation, and we can again consider this restriction of this gauge transformation on the sigma 3 sphere and the homotopy class. So this is G sigma eta is a map from sigma I, which is S3 to SU2, which is also S3. So we can consider this as a class of pi 3 of S3, which we saw earlier is isomorphic to Z. And so this gives us, so this will be our NIs. This is gives us a C as a zero cycle with coefficients in Z, and so it gives us a class in zero emoji of M Z, which is isomorphic to H4. Well, here this is what is called second. If we use this isomorphism, so the class which we got is what is called second check class. So in principle, one can, this part one can do generalize it easily to arbitrary dimension, but we need dimension 4 to say that this is a classification. So this is classified by, actually, so this invariant is a complete invariant in this case. This is classified by H4. Well, in principle, this is isomorphic to just Z to the number of connected component. Yes. Yes, so the question in chat, are the classification of direct strings done by, yes, so direct strings model kind of the deformations, direct strings modular gauge transformations are given by these elements. And the interpretation is that in terms of Poincare duality, this kind of the network of direct strings gives a d-2 cycle, which represents the class in the d-2 homology group, which is Poincare dual to this H2, yes. Any other questions? Okay. And okay, finally, let me consider yet another similar example. We consider SO3 gauge configuration M. And here's a statement that we can define what is called second Stiefel-Witten class, and this will be a class in cohomology with Z2 coefficients. And interpretation is similar to the one for the first chain class, so we can define H group A. Now it's one form on M with coefficients being in SO3 the algebra globally on M minus C. Again, this is a d-2 cycle. So these alphas are somewhat analogous to Dirac strings, and so we consider again alpha I and a small circle around it, and we say that so now we repeat the same thing as we did before, and we consider restriction of this gauge transformation on gamma I, and this can be chosen the map from S1 to now SO3, and the class of this map then lives in the fundamental group of SO3, which, as we saw earlier, is isomorphic to Z2. And this gives us the coefficients in this singular D-2 chain. And the same as that W2 is Poincare dual to the class of this chain. Okay, if there are no questions about this part, then I can, I don't know, are we supposed to do some sort of 10-minute break, or we can just continue until 6?
It is. Should I create a pool quickly? Yeah, I think we can continue to recover the minutes from yesterday.
Okay, yeah. Okay, the next part so will be about topological. So I'm kind of done with kind of this very informal introduction of basic concept in algebraic topology. So we consider it briefly as a notion of like homotopy groups, homological homology, and the notion of characteristic classes, and what is kind of the physical interpretation. And the next step is will be about what is called topological discrete gauge series. So the goal kind of to understand what are these discrete gauge series are, and what is their classification. So usually, first let us review kind of some basic basic concepts which appear in the kind of usual gauge theory, where the gauge group is continuous, which means it's some sort of Lie group. So what is the, in particular, what is the, so kind of, we have a gauge field. What is the notion of the gauge field? Continuous gauge group. Because in order to construct, kind of understand our theory, we have to first kind of understand what is our fields, what is our fields in our theory, and the second part will be constructing a kind of an action, which defines kind of both classical and quantum theory if we use path integral approach to quantum field theory. So in order to understand what should be fields in the discrete gauge theory, let us briefly review what is the fields and in continuous gauge theory, and what is the gauge invariant information contained there. standard example is something like E1 for Maxwell theory, or SU2 or SU3 for Young-Mills theory. And so the kind of this gauge field can be understood as something which defines parallel transport of local operators by fx. So, well, classically, a local operator is just a kind of value of the field at a particular point in space-time. And suppose they're evaluating some sort of vector space V, or it can be understood some sort of just sort of more complex n-dimensional space. And these fields, so this vector space forms a representation of our gauge group G in the representation rho of G. And so representation can be understood as a homomorphism from G to the group of endomorphisms V. So this means that for each G, we can define rho G, which acts on V. And yeah, for example, if V is just Cn, then this rho G is some n by n matrix. And what does it mean when we do parallel transport is the following. So we start with, consider kind of some fielded point x in our spacetime M, and we consider some path gamma to another point x prime. And we take 5x, and we considering what is called path ordered exponent of the integral of a along this path gamma. So this defines an element in my gauge group G, and then we take rho of it and act on it on our phi. And the statement is this transforms as phi of x prime. It's x prime is a point at the end, at the other end of my path. Well, what does it mean exactly? It means transform under gauge transformation. Gauge transformation is a map from my spacetime to my gauge group G, and under this under such a gauge transformation, phi of x goes to rho of G of x, and then if one uses well, basically the gauge transformation of the field A is such that if you take this, it will go to rho of G of x prime times the same thing as before. Okay, and So mathematically, our fields can be understood phi is a section of an associated bundle. So it's a for each, if we have a principal bundle and we have some representation of our structure group G, then we can construct the associated bundle where basically the fibers, each fiber forms a representation of this group G. Well, we can consider this kind of parse ordered exponent itself without any field phi, and this under gauge transformation transforms as well g of x. G inverse. So this itself is not gauge invariant, but if we take a trace of rho, so we consider now consider gamma to be a loop. So x is the same as x prime. You consider trace of this parse ordered exponent in some representation rho. Then this will be a gauge invariant, which can be seen immediately from the formula above. So now we want to take this group G to be a discrete group. For example, G is can be something like a cyclic group of order n. So what is analog of this path ordered exponent, or which gives me a parallel transform? Well, mathematically, this is what is called holonomy along a path gamma. Well, what we want again for each path gamma, we still want to assign from x and prime. We want to get some element of the group G. And if you have a pair of paths, and we can consider kind of a path which is a gamma, which is a concatenation of gamma 1 and gamma 2, it should, so the kind of the parallel transport assigned to this path gamma should be a composition of parallel transports assigned to gamma 1 and gamma 2. So A of gamma must be this well, this is here we mean a group operation G, and let me now assume that G is abelian. So this, and for abelian group we use a convention that the group operation is plus, it's denoted by plus. Well, the order here in abelian group, the order doesn't matter. We can write it this way. Okay. So this, well, gamma here can be understood, the path can be understood as a map from one simplex to M, right, to our space-time. So A, so this then assignment A, which we have, can be understood as a home from Cn. Okay, well here it's C1 of M. It's coefficients in Z. So it's a group which is freely generated by such maps M. So we can extend the value of A linearly to this group of singular one chains. But it's actually not an arbitrary. So A is this way. A can be stood as a one cochain of M with coefficients in G, but it's not an arbitrary cochain. So physically, we want some sort of requiring that if we change this path gamma a little bit, then this kind of holonomy shouldn't change. Should also change a little. So in particular, kind of this value should depend continuously on like if on this kind of on this space of paths. But if so this let me write in this way, a gamma should depend continuously on gamma. Well, but since it's valid in a discrete group, continuously means it's just a locally constant. So if you change gamma a little bit, this shouldn't change. The A of gamma shouldn't change. And then if you consider a triangle inside M, which is formed by gamma 1, gamma 2, and let's say gamma, so it's clear that we can relate this gamma to composition of gamma 1 and gamma 2 by continuous deformation. So, and this in particular implies that A of gamma should be equal to A of gamma 1 plus A of gamma 2. And if this is so this triangle can be understood as a singular two chain in M. And then this relation means that A of the boundary of beta is 0. But this is the same. This implies that delta of I of A is 0, since beta was an arbitrary singular two simplex. This implies that delta A is 0, because by definition, this is just composition of A is D. So this way, now we kind of we have an understanding as kind of discrete gauge fields is closed well, close meaning that it's co-boundary 0, one cocycle M with coefficients in G, our gauge group. But well, different cocycles can correspond to kind of different physical configurations. So the gauge invariant data as before, as in the continuous, in the case of kind of continuous gauge theory, is given by the values on loops. Gamma. And so what are the values on loops? Well, so it's values. So we already argued that it's only can depend on kind of, it should be invariant on the continuous deformation. So it should be actually depend only on homotopy classes of loops. But since if you take G to be abelian, we can replace this fundamental group with its abelianization. And there is a statement which is not difficult to understand. So this abelianization of fundamental group is isomorphic to first homology group of M with integer coefficients. And well, the relation is given and if we can consider basically, well, these loops can be understood as kind of singular one simplices. So the loop is a function from an interval to M. And this is isomorphic to the first cohomology of M with coefficients in G. So as I showed before, in general, there is this well, there is a natural map from the cohomology to the group of homes from the homology to G, but in degree one can argue that this is actually isomorphism. And I can understand, this class in the first homology group, we can understand as a class of this one cocycle A, which we considered before. So kind of, well, the bottom line here is the gauge invariant data given by some, oh, let me write it, I know, B plus of A. So kind of when you consider so yeah, gauge invariant field configurations, they're just given by the first the cohomology classes. And okay. Questions?
I don't see any.
So now we can kind of, in a sense, just say that, okay, our fields will be cohomology classes. Or the our fields are kind of mindful. So kind of, let me also mention, so kind of informally, this HP kind of MG can be understood as some sort of differential forms. P forms. So it's kind of informal understanding is based on DRAM theory. So we can, in principle, we can generalize it fields valued in piece cohomology. So yeah, one way to say this is just some sort of what we had here is some sort of motivation, but now we can just postulate, okay, let's consider some sort of theory where our fields are kind of co-cycles, singular co-cycles with coefficient of G, or we consider fields already kind of homologation summations, which are cohomology classes. So what is the so we previously we considered this notion of Poincare duality. So what is the kind of physical meaning of the Poincare dual class? Yeah, let me yeah, let me consider the case when p equals 1. But again, this yeah, this is can be generalized to any p in principle. So this H1, yeah, I'll mention a little bit about generalization later. So the Poincare duality tells us that this is isomorphic to H d minus 1 of M with coefficients in G. And this, as we saw already a few times, this is realized by classes of C, where C are kind of singular chains. And again, in the kind of, yeah, so these alphas on a smooth manifold, I can choose as alphas to be smooth functions. So let me, in order to kind of draw a picture, let's assume that d equals 3. So these alphas are, so they're maps from 2 simplex to m. So we have a network of some sort of triangles. Okay, the way we understood Poincare duality before, it works. Yeah, it works then in the following way. So if you now consider some sort of field phi in a representation V of G, which now is some sort of discrete group G. So it works in this following. So if you choose a parallel transport along some path gamma from x to x prime as before, so this so this so it's given by rho of a of gamma. So a of gamma. So a is represents cell class in first cohomology, which is related by Poincare duality with this C. So this is so a of gamma is what we use to replace this path-ordered exponent, the holonomy, and so if you recall how we kind of understood Poincare duality before in terms of this kind of intersection numbers, so it works then it's the following way. So so each time we cross some alpha I in this kind of network. So here, for example, we crossed alpha 1, then we crossed alpha 2. So we multiply by rho of ni. Right? So this ni is the element of G. So we have this Poincare dual is realized by this kind of network of, well, here it's two-dimensional defects colored by kind of elements of the group. And the parallel transport of our current field and some representation works in the following way. So if you kind of take this, start moving it, so in general, nothing happens. But as long as we cross is kind of, we go along this path, as we cross one of these defects, we multiply this phi by rho of this kind of the group element associated to this to this particular defect. And this gives interpretation of this of C as a network of what in physics called charge operators. And those who are following this kind of generalized, all this generalized symmetry story, they probably heard that these charge operators are kind of essentially the same as topological defects in general. And so why so maybe yeah, so yeah, we'll I probably want to explain a little bit more on this, why these defects have an operation of charge operators, but yeah, we have to finish soon, so I'll do this in the next lecture. But well, the basic idea is that yeah, I will probably repeat this in the next lecture, but the basic idea is that the kind of usual charge operators works in the following way. So if you consider kind of quantum operators corresponding to the field, so we have a kind of, you have a unit of transformation corresponding to some group element G. This is acts the following on my field operator phi, but one can rewrite it in some sort of, in this way. And this means this can be interpreted as kind of commuting this U operator this phi operator gives me a multiplication by rho of G. And well, and this exactly is kind of analogous to what we just had about this crossing, right? So we have this kind of phi and UG. So we can exchange U with phi. So we can use the fact that kind of if we insert operators in the path integral, they are kind of positioned along one of the directions, like time direction, is consistent with the ordering of kind of the operators. So we kind of exchange this U of G with phi, and this gives me kind of extra. So this is what we had before, where G was essentially this one of the NIs when we crossed. Can interpret this as one of these A alphas, and this is one of the A alphas. Yeah, I will probably mention this repeated more carefully next time, because I have to finish now at 6 p.m. So yeah, that's it for today. But yeah, if you have some questions, let me know.